Okay, good morning, everyone. Let's get started. It's nice to see everyone. For those of you I haven't met before, I'm Ed Blucher. I'm the director of the Enrico Fermi Institute that hosts these lectures. So I want to introduce this fall's lecture series that I'm really excited about. Those of you who were around last year know that I had been talking about the idea of having a series on this topic for a while, and we found a perfect person to do it. So Anthony Badea was an undergraduate at MIT. He got his PhD in physics at Harvard. And since 2023, he's been an Eric and Wendy Schmidt AI and Science postdoctoral fellow and research scientist in the Enrico Fermi Institute. So he works in experimental particle physics that he'll be talking with you about, and specifically does lots of work on applications of AI to science problems. So I think it's going to be a fascinating series that I hope all of you enjoy. Okay, thanks. Anthony.
Morning, everybody. So I guess first, Mary, is it okay up there? Okay. And then can I get, let's make sure. Okay, great. So I'm Anthony. Like I said, I'm going to be talking to you about understanding the building blocks of nature with particle collisions and AI. And this is the first of a sequence of lectures. And in this, we're just going to give a high-level overview of what we're talking about, some general ideas, and then lay out what we're going to talk about for the next 7 lectures. But first, what I wanted to do was actually have a round of applause for Ed and for Mary. They actually put a lot of work into this. And so Mary's in the back over there and has done a lot. And they helped me a lot in coming up with the idea and working through it. And then the next thing I want to do is kind of do a shameless ad for the previous 2 lecture series. So the past one was Chris, and it was Philip before. And all of these are available on the website. So when we post the slides, there'll be a link up here where you can go and see them. And so Chris talked about the largest scales of the universe, so astrophysics, looking with cameras all the way up at the cosmos. And then Philip, who is a particle physicist like me, talked about science and technology and how the combination of both of them have spurred on innovations in both. And so then when I thought about this lecture, like I said, Chris talked about roughly the largest scales in the universe, and Philip talked about science and technology. And so kind of what Ed was saying was it somehow feels fitting to do a series where we talk about particle physics and AI. And why that feels fitting from a physics perspective, so this is my favorite plot in all of physics. And what this is a history of the universe. And along this axis here, you have the time since the Big Bang. So you have all the way down here, right at the earliest moments, post-inflation. And then you have an evolution as the temperature of the universe cooled down. And then up here, you have what experimental programs we conduct to actually probe these different time periods. And so what Chris talked about is the largest scale, so understanding the galactic scales and understanding how physics leads to the universe around us. And then what Phil talked about is how science, technology, the merging of them, has enabled us to do that study, has enabled technology around us. And now what I'm going to be talking about is the earliest scales, the small scales that we can see, quantum mechanics at work, and how technology is allowing us to do this. And so my broad interest, like I said, is in this time period here, which is just after inflation. So the universe had some really fast expansion. The accelerating universe continued, and then we started to cool down. And as we cooled down, fundamental particles started interacting, and this is even before we had nuclei form. And why I'm interested in this is that the small scale dynamics, how these very basic building blocks interacted, leaves an imprint on the universe around us. And so things like interaction of dark matter particles, Higgs boson particles, they interact at this earliest time, and they leave an imprint. And so how I got there, I wanted to give a little shout out to people that taught me a lot over the years. So I had a really great advisor at MIT named Yenji Lee, and he was the one who really got me into particle physics experiments. So there's kind of 2 branches here. There's the theory aspect and the experimental aspect, and I'm an experimentalist, where I like to do things on Earth in controlled situations to understand how the building blocks formed. And so Yenji was really interested in this period here, this slice right here, where what we do is we try to create on Earth a system where you have protons and neutrons melted down even before any sort of chemistry kicks in. So Yenji got me really interested in doing actual on-ground experiments to probe this time. And then John at Harvard, who I just saw not too long ago, he got me interested in an earlier time period where using similar types of techniques, you can actually probe a whole order of magnitude earlier in the universe, a whole order of magnitude higher in temperature. And so then if I make the connection to what we're going to be talking about here, increasingly nowadays, particle physics experiments are becoming basically synonymous with massive data experiments. And so what this plot is here, I'll show this a few times. This is an example from the experiment that I work on, the ATLAS experiment, which is at the Large Hadron Collider in Geneva, Switzerland. And along the x-axis here, you have year, so 2000, and then XX. So this is 2010, 2045 with some projections out. And this is since we started taking data. And then this axis here is the intensity that we run at. And none of these really matter. The thing I really wanted to highlight is this purple curve. And so this is a curve of the amount of data that we produce as a function of time. And then the horizontal axis, the horizontal line that I put here, is the total amount of data on the internet as of 2024. And so where we are right here, you see we're less than 1/8, 1/6 of it. So to actually do the physics that we're talking about, we produce an enormous amount of data. And it's not just that we're producing data for the fun of it so that we have jobs and we can analyze things. We're actually doing it because the physics necessitates it. And so the whole idea behind this lecture series is that in order to get the physics we're interested in, we have to produce huge quantities of data. This has led us over the years to use new computing methods. And in particular right now, AI is at the lead of this. And so like I said, this was what Ed called me and talked about. So this is Ed, like I just said, and I like to think of him when he's at the experiment that he's building, the deep underground neutrino experiment, where he's in a shaft and they're excavating this huge mine and they're putting this massive experiment under there. So I like to think that he was there when he called me, but I know he was actually at his desk. And I tell him that I was at CERN doing hard work and not just sitting here having an espresso. And so he called me and he put this idea out there about what if we do a lecture series about the current state of particle physics. So the LHC has been running for 10 years. A lot of other experiments are happening. We're projecting forward. And then about how AI is being used on the ground. So not just how AI is being used in the media, how it has this huge promise, but how we're already using it to make important measurements. And so that's the idea behind this lecture series. And so for the next, roughly how I'm going to divide each of these is there are going to be 3 sections. In the next ones, I'm going to do, the beginning will be some refresher on what we talked about, and then I'm going to have a general topic for each section, and then we'll make connections to where the next lecture is going. And so then for the next section of today, I just want to flesh out a bit longer why particle physics, why AI, and roughly the logic at the end, what I'm hoping you understand is that to get to the physics that we're interested in, we have to do many, many high energy particle collisions, and we have to analyze enormous quantities of data. And so the first thing I want to do is actually go back a little bit further and talk about the scales that we're interested in. So over here on first the axis that we're talking about here, this axis here is in scales of meters, and all the way over here, this is 10 to the minus 9th, so this is 1 in 1 billionth of a meter. And this is roughly the atomic scale. And then as we go further and further down, roughly 4 to 5 orders of magnitude, we get to nuclei. So composite particles formed of neutrons and protons. And then if we go down 2 more orders of magnitude to the femtometer scale, we get to protons and neutrons, which are nearly fundamental particles, but still composite. And we go down another at least 3 orders of magnitude, where I put a less than or equal to here, because it's still not known if these are actually built out of other types of particles. We get the smallest irreducible pieces of matter that we've currently found. So from all different experimental approaches, we haven't yet been able to split these any further. And so this is what builds up everything else around us. And so our objective is to study these particles and all of their interactions via forces. And so of course we've been doing this for quite a long time, I'd say roughly 100, 150 years. And the culmination of that has resulted in a theory of nature called the Standard Model. And this theory of nature is described by fundamental particles and how they interact via forces. A familiar force can be electromagnetism. There can be the strong force, like what binds together protons and neutrons. But the point of this is that there is a description where you have a certain number of particles, and that number of particles is 17 right now. So in white here, you have the so-called matter particles, which make up what we see around us. So important ones that I'll point out, so these are the so-called quarks, and these up and down quarks make up the proton. And then you have the familiar electron, and then you have heavier copies of each of them. And then down here you have neutrinos, which is what Ed is helping build this massive experiment to study. And then in the colors, we have the particles that mediate forces. So when we talk about electromagnetism, for example, there is a particle known as the photon that is actually what carries light and interacts charged particles. And then we have other ones called the gluon and the W and the Z bosons. The gluon is what helps glue together, as the name goes, protons and neutrons. And then the W and the Z mediate nuclear decay. So things like nuclear fusion inside of the sun, these are extremely important. And then we have one particle that ties it all together that we'll talk about more later, called the Higgs boson, which we observed at the LHC for the first time 10 years ago. And so in total, all of this puts a description and puts a formula for how we can actually understand the universe. And an important note of this is that the underlying theory of this is really a merging of two pillars of physics. So it's a merging of quantum mechanics and of special relativity. It doesn't include any sort of gravitational source, and it doesn't include any aspects of large-scale dynamics. And so the point that I really want to emphasize here is that what we do is we tune the theory with experiment. So all of the particle masses, all of the couplings in here result in roughly 26 free parameters, and we do experiments where we tune all of them. And so, like I said, the theory has been wildly successful. I'll show you a slide in roughly 2 slides, I think, where I show you just how successful it's been. But there are a number of open problems, and so in general, we know that the theory is incomplete. I think the most obvious of that is if you just look at this plot here, my favorite plot, you can basically go each time slice and say, can we actually make a computer program that simulates all interesting things of this? And the answer is no. We do not know how to take the basic equations that we write down and do a full-scale simulation of the universe. We do not know how to answer very basic questions from the experimental side. So, for example, we still don't know what the particle nature of dark matter is. We only have a description of it from cosmological and astrophysical measurements. We do not know why the standard model doesn't include gravity. We don't know how to merge them. And we don't know other basic things, like if you look out in the universe, you see predominantly matter and not antimatter. So you see more protons than antiprotons. And we have very precise experimental measurements for that. And so there's a whole host of problems that point to the need for new physics that are outside of the standard model. And so what do we do to try to answer that? Well, other people take different approaches, but the approach that I work on is particle collisions. So the general idea here is we take particles of different species and we want to create the conditions to see them interact. So this is to say, if you take 2 electrons and you throw them at each other, what are all possible ways that they can interact? What are all possible things that can come out? Why is this? How does this tie to the early universe? Well, in the early universe, you had basically a soup of energy where you had particles coming in and out of existence, and all possible interactions could happen. So that's what the experimental aim is. So we shoot in protons, bags of particles, we shoot in nuclei, we shoot in electrons. There's other ideas to shoot in different types. We shoot them in all sorts of different configurations, and we see what comes out. And so just to emphasize that point of what we've done over the years and what the different scales we're talking about, so electrons and positrons, the antiparticle of the electron, basically point like. We shoot them in at very high energies and we can do really precise measurements. And then we've done over the years protons, antiprotons, nuclei, antinuclei, and we've even done combinations of them. So protons on nuclei, electrons on protons, electrons on neutrons, electrons on nuclei, all sorts of different combinations to teach us different things about the interactions. And so we've had a rich history of doing collisions of this type. So this is another very famous plot in particle physics, where along the x-axis here, you have the year of first physics. This is the so-called Livingston plot. And along the y-axis here, you have the energy scale of the collision. And the units are not super important, just to know that right here is roughly the energy scale of the mass of the proton. And then we go up roughly 5 orders of magnitude. This red line here is where we collide electrons. This black line here is where we collide protons. And you see that over time, spanning all the way from the 60s up till now, we've gone on this progressive trend to reach higher and higher energies. Now, why we're doing this is because as we ramp up the energies, we're able to probe higher mass objects through the famous E equals mc squared. So we pack a lot of energy into a very small amount of space, and we convert that energy into mass. So this is a pillar of relativity, special relativity. And then we're also able to probe smaller and smaller distances, which is exactly where quantum mechanics becomes important. So this equation here is a pillar of quantum mechanics, where you have energy is inversely proportional to the length scale that you're probing at. So as you go to higher energies, you can probe smaller and smaller physics. And over the years, this approach of colliding at higher and higher energies has led to important discoveries. So we found the W and the Z bosons at CERN around 30 years ago. 40 years ago, we found the top quark nearby at Fermilab in the 90s, and recently we found the Higgs boson. And each one of these discoveries had led to Nobel Prizes and all sorts of important information about physics. And so the example that we're going to be talking about is the one that I work on right now, and the one that has been in operation since basically my entire lifetime. This is the Large Hadron Collider. And so this is a 27-kilometer long particle accelerator that exists on the border of Geneva, Switzerland, and a place called Saint-Genis, France. And so this is Lake Geneva here. These are the Alps in the background. And underneath this farmland is 100 meters underground is a particle collider that looks like this. So there's a tunnel, and inside that tunnel, there are 2 counter-circulating beams of particles, protons and neutrons. And we ramp them up to protons and nuclei, and we ramp them up to extremely high energies. And then at 4 points, we collide them. So this is the experiment that I work on. I've spent time thinking about this experiment in the past, and there's other specialized ones over here. But just to emphasize, this is the highest energy collider that has ever been built. It is a multi-purpose collider where you can shoot in protons, you can shoot in nuclei. We've not just shot in one type of nuclei. We've shot in lead nuclei, xenon nuclei, and we're hoping to shoot in oxygen also. And doing this, we really get particles nearly to the speed of light. I think the last time I did the calculation, it was something like 99.9 with 5 or 6 9% the speed of light. And so if we take a snapshot of each collision, the anatomy of a collision is very interesting. So we have these 2 incoming beams of particles. For this case, I drew 2 protons, where you have the quarks inside of them. They come in at such high energies that you're able to see what's actually inside of them. They come in, and then you have some sort of primary interaction. So in this case, I drew these squiggles, which represent a different type of particle known as the gluon. And you have a primary interaction where 2 of them collide, and then through E equals mc squared and a quantum mechanical process, you end up with a bunch of final state particles. And so what we're interested in is studying all possible things that can happen inside of this blob. And the important thing is that what can happen inside of this blob is directly tied to the properties of the incoming particles, so the fact that these are protons or if they're electrons or nuclei, and it's tied to how much energy is available here. And so now this is probably my second favorite plot in all of physics. This is a plot which is showing when you shoot in 2 protons, what are interesting processes that can come out. Maybe you shoot in 2 protons and then you produce a Higgs boson. Maybe you shoot in 2 protons and you produce pairs of W bosons or 4 top quarks. So this is interesting process along this axis. And then along this axis is roughly the probability to make it. And so this probability is entirely derived from quantum mechanics, special relativity, and experimental input. And the thing I want to point out is the different colors here. So first, this is the theory prediction. So this is if we take our basic formalism and do large-scale simulations and ask from theory, what is the probability to have these interactions? And then these lines here are 3 different set of measurements from doing the experiments at the LHC. And now the color schemes, all the dots I know are way too small to even see. I mean, for me, they're even too small. And the important part is that basically every dot is on top of the theory prediction. And to emphasize, this is over 13 orders of magnitude. So over 13 orders of magnitude, over 3 different energy scales, the theory predictions match the experimental results spot on. This is roughly 100 years of theory and experiment culminating into being able to describe every single possible interaction that we have on Earth inside of one plot. But for today, the actual thing that I wanted to point out is this, if we take a snapshot at this number 1 here, which is in some arbitrary units, a probability, and ask how many billions of collisions do you need to get a single one of these events. And so the rough number to get one event of this, you need 100 billion collisions. So you have to shoot in protons and have them hit each other 100 billion times to just get one of these. That doesn't say anything about if you can measure it. That doesn't say anything about if your detectors are tuned to be able to capture it, if you save the data, if you can understand the data. It says none of that. It just says in order to get a single one, how many times you have to collide 2 protons. And that number is roughly 100 billion. And so then if you look at the experimental program that we're doing, the whole goal is probe the rarest processes that we can make. And so to do that, we have to generate billions and billions of collisions. And so this is the same plot that I showed you earlier, where along the x-axis, it's the year since operation. Along this axis, it's the intensity, the peak intensity of collisions. So how many collisions roughly per second are you doing? This is the integrated amount of data. And now instead of showing gigabytes, I'm showing billions of collisions. And this scale here is from 1,000 billion all the way up to 1 billion billion. And so as of 2024, roughly 14 years after the start of the LHC, we've done around 35 million billion collisions. And over the next 10 years, we're projected to roughly multiply that by 25, maybe even more. And to emphasize, the point of this is that in order to understand the rarest processes on this plot here, where we're interested is rare decays of Higgs bosons, rare production of all sorts of different exotic particles, the theory necessitates us to do huge numbers of collisions so we can really sample this steeply falling probability distribution. And so that's why we're going to huge, huge amounts of collisions. Now, around every collision, we want to actually be able to take the data. So what we do is around 4 points, we place very sophisticated detectors. Now, these detectors are similar detectors in other places. There's some differences. And so this is a plot, this is a picture of the experiment I work on. This is the ATLAS experiment. And the red lines that I drew here are where the beam is coming in. So this is the LHC beam pipe. And in the center here, you have particles hit head on, and then explosions of particles come out. And for scale, this right here is a person. So it's an enormous experiment. The physics necessitates that the experiment be big so that we can actually detect particles of different species. And so this on the right here is a cutout of the experiment, where the important lines to see is that each one of these lines is showing how a different type of particle, whether that's a photon or a proton or an electron, interact with the different pieces of the detector. Now, for today, the only thing that's important to know about this is that these detectors effectively act as high-resolution cameras. You take really detailed pictures of the earliest moments of the collision all the way down to the millimeter scale. And then what we're trying to do is use these pictures to reconstruct what actually happened early on. And so each one of these pictures, you can ask how much data is each picture. And the number currently is somewhere around 2 megabytes of data per collision. And so then we get to, or first I want to show what one of these events can look like. So this is, instead of colliding 2 protons, this is 2 nuclei, so 2 lead nuclei. And this is actually a plot that I've been making not too long ago, maybe a week or 2 weeks ago, and that I was bugging Ed a lot and sending him pictures of this and showing it to him. So these are 2 nuclei come in, and they smash right here. And now every line that you're seeing and every block that you're seeing is a different piece of the detector light up. So it's a particle moving through, leaving energy deposits, and then exciting charges inside of that piece of the detector. And so actually what's happening in this one is you have 2 nuclei come in, and then out comes 2 highly energetic particles. So this one is an electron, and then you have these jets of particles that come out. And so each one of these type of images is roughly 2 megabytes. And so then we can get the plot that we had earlier, where we go from billions of collisions to total amount of data. And so this is now that same plot, where this is the line that you saw just a few seconds ago, where it's billions of collisions. This is the line that you saw earlier, where it's gigabytes of data. And so you see they closely track each other, because all that we're doing is just taking this green line and multiplying it by gigabytes per collision. And so then you really end up in a place where you have so much data produced that you have basically no idea how to handle it. You have to use extremely sophisticated computing platforms and algorithms to actually handle it. And so this is the core idea of where AI comes into play. And so computing in particle physics, like I said, they're kind of synonymous. We've been using computing for a very long time. So for example, at CERN in 1989, the World Wide Web was found. And so if you ever have the chance to go to Geneva, you can actually go see the office where the World Wide Web was invented. And in that office, we've done some PR where we got an old computer and kind of set it up so you can think that it was made on there. So it's kind of fun. But the point is that computing has been deeply ingrained in the particle physics community for a very long time. And AI and ML and related hardware are the newest ideas of this that are used at wide scales already. So I think if I was giving this talk maybe 10 years ago, it would be the early days of when things were being adopted. So there are algorithms that were running 10 years ago. For the Higgs discovery, there were algorithms that were running. But really wide scale, where all pieces of the experiment AI is used, this is really the time is now. And so then I wanted to talk a little bit about what I've heard and kind of where our focus is going to be. So if I make axis here, which is roughly physics plus AI, and I put what I hear in the media, dreams, and maybe reality, and then what we do every day on the ground. So all the way up here, I hear maybe sometime soon, AI gives us a theory of everything. So this is basically, it looks at all of our data in one shot. It somehow does infinite numbers of PhDs in one shot, and it just spits out a complete theory. So I think that this is pretty far away. And then there's dreams. So maybe you can interpret the results and then predict new experiments. So for example, we're talking about, I think I talked to some of you about the next generation of the LHC, and we're currently discussing what that will look like. And there's ideas of maybe we should use some sophisticated algorithms like AI to actually look at the data and inform us of what we should make the next experiments as. This I don't think is actually all that far away. And then similarly, full-scale simulations of this standard model. So this theory of nature that we have, we're really only good at simulating it in approximations. We can only do it at certain scales. But a lot of these new methods are opening up the possibility to really simulate the theory from first principle. So I don't think that's that far away. And then the third one is real-time analysis, where when we produce this enormous quantity of data, we actually can't save all of it. And so I'll talk a little bit about that. But there's an idea that maybe we can get algorithms running fast enough and on dedicated computing platforms like GPUs or FPGAs, where we can do analysis in real time. So basically, right when you do the experiment, forget waiting 5-10 years to get the results, you get the results immediately. I don't think that any of these are actually all that far away, but it requires adopting a lot of new techniques. And then there's every day on the ground. So I think every day on the ground, the best way I could put it is we're improving the experimental capabilities to trigger, which is select events that you're interested in, to identify particles, so know if an electron came out or a proton came out, reconstruct events. If we have 2 protons come in and then a whole, like thousands of particles come out, we want to know what happened at that primary interaction. So actually being able to go from meter scales, which is where the detectors are operating, down to femtometer scales, which is where the interactions happen. This is being facilitated now by ML. And then last, simulation. And by simulation, I mean something different than fully simulate the theory. I mean, as we ramp up the experiment to collect more and more collisions, the ability to compare the experimental result with the theory requires that we do tons and tons of simulations. And so I can make a similar plot, which is from that gigabytes of data, which is amount of computing time needed to generate enough simulation that we can compare with the experiment, and you'll get a very similar result, that you basically need more computing than we really have access to. And so then if I go back to Ed's call to me, this is what we're going to be talking about. So we're going to be talking about every day on the ground, how this is being used, and how it's facilitating experimental measurements.
Can I ask?
Yeah.
When you say AI,
Yeah.
are you automatically including quantum computing?
No. No. So that's a good point. I think if I go back, and probably I should have mentioned it more, when I say newest wide scale used, there are currently programs to use quantum computing in different ways. So far as I understand, the quantum bits, they effectively decohere too fast, where they're not reliable enough, and they're not tuned to the problems that we're interested in yet. So the devices just aren't good enough. And at CERN, there's a lot of work on trying to adapt the existing devices to actually do that. But right now, they're too early days. And so when we say wide scale, we mean we're basically, if you're doing a PhD, you have to use this. It's at every stage of the experiment. Everybody needs to learn it. It's just like maybe 20 years ago when everybody needed to learn how to program in order to be on the experiments. Yeah. And that was actually a good point. I was going to pause and say, are there any other questions? Because the next part, I'm just going to go into a little bit of where we're heading for the next few lectures. Yeah.
So you said something early on that the work is the result of the standard model being the result of the merger of quantum mechanics and special relativity. And then several times you referred to the part of special relativity that gives the mass energy equivalence.
Mm-hmm.
And you pointed out where that occurred in one of those drawings.
Mm-hmm.
So I've always understood special relativity to involve other things, including time dilation, and I don't know what else. But could you say anything else about what it means to merge quantum mechanics and special relativity
Yeah.
with some reference to these things that we can understand
Yeah.
what you're talking about?
Yeah. So what we mean is quantum mechanics is telling us at the very smallest scales, so at the scales of electrons, protons, what we should expect from interactions. So it's a descriptive theory. Then when we say we merge it with special relativity, we're interested in what happens at really high speeds. So at the highest speeds possible, near the speed of light. And so then that's when you need to take quantum mechanics, which is a non-relativistic theory. So when you start talking about time dilation and all of these things, you're going into a relativistic domain. We're really fast. And you have to make the theory relativistic. And so then things that happen is you start to get behavior near the speed of light where you can get particles where their lifetimes are longer from time dilation or other effects like this. Now, the important thing that I think to say is why I don't go further and say general relativity, which is a bigger version of special relativity, is the standard model is not including gravity. So the gravitational source, which is on the large scales, we don't model that at all inside of the standard model. And there's ideas for a way to do that. Maybe there's a new particle that mediates these interactions. But so far, we have no good description of that. And kind of the place, I think, that maybe you've heard about this is a very interesting domain that people study now is what happens right on the edges of black holes. So right on the edges of black holes, you get a place where you have extremely high energies, you have extremely high energy densities, and you're really probing large scales with high energies. So it's right at the intersection of general relativity, gravity, and quantum mechanics. And so right there, you get interesting things. But for us, we're just really talking about quantum mechanics at really high speeds, which is the particles that we're talking about. Yeah?
When you say mass converted to energy or energy converted to mass,
Yeah.
so if the mass is converted to energy, the mass disappears?
Yeah.
Or does it, or is it really transferred from the quantity, okay, into the space,
Right.
and it's still, it may exist as mass, or does it really disappear completely?
Right. So I think this is going to go into a little bit more philosophical. So I'm going to keep it in like roughly language that I can use in the experimental side. When I say a transfer of mass into energy and back and forth, I mean if I shoot in two electrons that have mass, when they collide and we convert the energy, we convert their mass into energy, those electrons disappear. Now if you start talking about, yeah, their mass converts totally into energy, which is sitting in some sort of field, and then out of that, new particles come. So that's the experimental version. If you start talking about a theoretical description of it, you can go down a bunch of different rabbit holes. Rabbit holes that I kind of like. If you imagine that roughly what's happening is you have a bunch of fields, like quantum mechanical fields, where particles are just energy waves sitting on that field. When you start smashing them together, there was never really a true description of energy or mass. They were kind of always going back and forth. And so when you have them two particles come in, the mass just drops back into the field, and then out comes two new particles. So experimentally, I think the answer is the particles really disappear. You shoot in two electrons, and they're really gone.
So the mass can be created and can be annihilated?
Yeah.
It can.
Yeah. Yeah.
So you talked about detecting some very rare events.
Yeah.
My question is that probability, that lower bound, are we reaching some lower bound so that only our ability to detect will improve? Or will the theories keep on getting richer and richer so that this probability gets even smaller and smaller and we can never reach that?
I wish I knew. I don't know. That is, at the root of the question is, if we keep probing rarer and rarer processes, will we ever get to a point where the theory breaks down? And will that point be accessible on Earth with our current technology? I have no idea. The goal is we want to get to that point. The entire goal of this program is try to break the theory, get to a point where we can see the experiment deviates from the theory. So I wish I knew. Yeah.
I'm interested in, can you hear me?
Yeah.
I'm interested in the interplay between the AI and machine learning, given that we still have problems with the qubits and the problems that being involved. Could you say a little more for a lay person like me?
Yeah.
Taking this data and feeding it into
Yeah. Yeah, so I think there was two things in your question. There was one question which was about, there was one which was about qubits, if I heard you right, and then there was one that was about AI and ML, and roughly the intersection of them. So I think for us, we want to separate these two ideas. So qubits, what people are trying to do with those is invent a new type of computing platform. So the same way that you used to see pictures of computers in rooms where they would take up the entire room, you can go to IBM and see a room where a quantum computer is sitting, where they're trying to do different types of computing on it. So really changing the way that we process bits. What we're talking about is using the classical computing methods, so GPUs, CPUs, like what you would have at home, but to do large-scale, effectively, computations on our data sets. And so what that means is you could go to Best Buy and you could buy a graphics processing unit, or you could buy a computer, and you could take our data and run it exactly on your computer. And in fact, that is actively what people do. All of our data we put on the internet now. Most of it we put on the internet now. And so you have plenty of people who are at home taking the data, they buy their own little computer, and then they can play with it too. So those are roughly the two domains that we're talking about. In different lectures, what I'll talk about, where we're heading, I'll give some more concrete information about what the data looks like, and then how we actually feed it in. Yeah.
Thank you.
Yeah, of course. Yeah.
You know how you were saying that you have to do like billions of collisions to get those rare events. What makes them rare events? Is it there's so many parameters and you have to the parameter right to see it, or is it something else?
Yeah, so let me rephrase your question and you tell me if I'm asking the right thing. That plot where I showed interesting processes and then probability, you're saying why are some of the processes so rare? It's actually asking why is the probability small? Yeah. So I think it'll take too long to go back, but if we looked at that plot, the rarest processes are basically translating into particles with the highest masses. So the biggest objects, the most massive objects. And what that means is that you have to have a ton of energy packed into a very small space to actually produce this high mass object. So that's one thing. Then the second thing is the coupling, which is when you shoot in two protons, maybe the electric charge of them will couple to another electrically charged objects. So two protons can come in, and then maybe at the end you end up with electrons. That coupling changes depending on the process that you're interested in. So for electromagnetism, it's this famous 1/137. For the strong force, it changes with energy scale, and where we're at the LHC, it's roughly 0.01. So that coupling changes also. So it's really two things. You have the coupling, and then you have the energy scale, the mass of the particle. Now, did that kind of answer or not at all? It could be not at all.
So you're saying it's maybe limitations in the experimental equipment?
No. So the answer was not at all then. No, so maybe it would help if I go. Yeah. So I'll give you a good example on here. So say I take this particle here. This particle, the Higgs boson, has a mass that's around 125 times larger than the proton mass. So in order to produce that, you need 125 times the mass of the proton into a very small area. So that's one thing. So you have roughly the impact of that goes like 1 over the mass squared. And then you have a second thing, which is the coupling between the Higgs and, for this case, I can call it the protons, can be really small. So that's to say, even if you were at really high energies, much higher energies than the Higgs mass, you would still need to have a coupling between two electrons or two protons that go in to actually get the particle at the end. And the combination of these results in these low processes. So it is completely independent of the experiment. Where the experiment does come in is you can ask, can the experiment actually produce this? Is there enough energy to produce it? And so when we start talking about things that are further down, so if this is 10 to the minus 2 in some arbitrary units, we talk about 10 to the minus 5, I would say the experiment couldn't produce this right now. Or if we were talking about things that instead of 125 times the proton mass, we said 1,000 times, 2,000 times the proton mass, we couldn't produce that right now. Okay, we could talk about it. Okay. Okay, so now I think we have maybe 10 more minutes, and I just want to give us a preview for where we're heading. So there's going to be 7 more lectures, and we'll discuss the big picture physics questions that are motivating this. We'll discuss examples of AI being used on the ground. We'll connect that knowledge with other experiments, and then we'll discuss some future directions. So just to summarize today, what we talked about is a very high overview of particle collisions, how doing the physics program that we're interested in, we require billions of collisions. These then translate into enormous amounts of data. And using that data, we get pretty pictures like this, where we're trying to make sense of all of these collisions to actually understand something about the universe and something about the fundamental interactions of nature. And then, so this is, again, the plots that you saw earlier. Next lecture, so this is going to be on October 12th, so same time next Saturday, we're going to talk about the big physics questions. So 10 years after the LHC has been running, what do we actually know about this picture here? Okay, this is a cartoon, but how much do we know about this? And what questions are still open? What are we still trying to answer? So we'll probably touch on some aspect of dark matter, some aspect about your question about the merging of relativity and quantum mechanics. We'll talk about the matter-antimatter asymmetry. We'll try to give a high-level physics motivation for why we're doing the experiments, and then hopefully at the end you can decide if you think it's worth it or not. And then we'll translate those physics questions into experimental needs. So we'll go from, for example, if you want to produce or measure dark matter in the lab, what type of experiment do you actually need to run? What does that translate into in terms of a collider? So we'll use the LHC as an example for the type of experimental constraints. And what I'm hoping we gain from this is an understanding of if you see something about, say, Ed's experiment when it turns on in 10, hopefully not 20 years, in some amount of time, of what type of physics they're trying to do and how that's then led to the experiment, that you'll have some intuition for how to translate between those languages. And the other thing I want to do with this is understand the data sets that we're talking about. To your question in the back, I want to understand a little bit more about the data sets, what they actually look like, and how they then fit into a computer. And then we'll go on 3 examples from the LHC where we have AI being used every day on different types of computing hardware. So the first thing we'll talk about is particle identification and event reconstruction. And this is roughly the ability to identify particles. So identify if it's an electron or if it's a proton, and identify, say, if it's a Higgs boson too, and to reconstruct the events. So pictorially, what you see here is a cross-sectional view of one of our collisions, and you see these 2 jets here. And now I know what this collision is because I've looked at it a lot. These are 2 heavy quarks. And actually being able to identify that these are 2 heavy quarks is extremely important and something that we've improved using machine learning over the years. And why I'm showing you this plot is because once you know that these are 2 heavy quarks, you'll be able to understand that this event is actually one where a Higgs boson is produced. And so using these methods to understand the particle properties, we can do event reconstruction where we can make sense of events like this and events like this. And so in this lecture, we'll start introducing the different types of computing platforms where we'll reintroduce CPUs, and then we'll also talk about GPUs a little bit. And then after that, we're going to talk about real-time event selection. So what this is I said, remember that we're producing so much data, so much data per second. I think the rough number is around 60 petabytes of data per second. But we only keep around less than 0.01% of it. We do not actually have the capacity to store all of the data. And what that means is that we have algorithms, so-called trigger algorithms, that are run in real time as the experiment's going to pick what data we save and throw away everything else. And I emphasize throw away everything else because I don't mean throw away like save less of it. I mean really throw it away. It's gone forever once the collision passes. And so what you see here is a picture. So this is actually our experiment's run coordinator who sits in the control room with the experiment and makes sure all the data collection is going well. And then what you see here are the trigger racks where you have actual hardware, so whether that's so-called field programmable gate arrays or CPUs, tons and tons of computers, so this would actually go well beyond the screen, and then wires that connect directly from the experiment inside the cavern all the way to these dedicated machines where algorithms are run, where we decide what events to keep and throw away. Then after that, we're going to talk about the third example, which will be simulation. So we want to, like I said, we want to do precise measurements, and we want to have comparisons with theory. We want to do this for billions and billions of collisions. In order to do that, we need to take this basic description of nature and convert it into what happens when protons collide. And so this is a nice graphic made by someone on our experiment, where it's our experiment roughly on the outside, and if you look closely, all the particles that are coming out are actually ones and zeros like bits. And so what we need to do is do this conversion from here to here, and we need to do it at really large scales and fast enough where, for example, a graduate student can do it. So instead of just us sitting there for 20 years hoping that we get enough simulation, we can actually do it in a reasonable amount of time. And then after that, so those will be 3 examples from the LHC, the experiment that I work on the most. And then we're going to try to connect what we've learned there to other experiments. So in particular, other upcoming experiments. So I'm going to leave this a little bit open based on how we're doing for the previous lectures, and if I feel that there's some interest in one direction or the other. But roughly the idea is that we're going to talk about the two basic big flagship particle experiments that are going to come up in the US. One is the electron-ion collider. And what this is that you shoot in an electron. So instead of like the LHC where you shoot in 2 protons, you shoot in an electron and it hits a nuclei target. And doing that, we're hoping to get a picture of the proton. So a 3D image of everything inside the proton. So that's one. And then I may embarrass myself in front of Ed and talk a little bit about the deep underground neutrino experiment, which is being built just nearby at Fermilab, where instead of shooting in protons, instead of shooting in electrons, we shoot protons in at a nucleus. From that nucleus, we get different types of particles coming out, and in their decay, you get a certain type called a neutrino, and then they'll shoot that neutrino beam through the rock from Illinois all the way to North Dakota, underground around 700, 800 miles, and then measure the particles over there. And so we're going to expand on what we've learned about the AI methods on the ground and see how they'll actually be deployed for the next generation of experiments going forward. And then in the last one, we'll talk a bit about outlook and future directions, where in here, this will be the opportunity to talk about things that are beyond the scope of just what's being used on the ground. So go from this deployed every day to kind of dream territory. And that may include new types of chips. So I work on with a few other people here and neighboring at Fermilab, where we build chips, where we put machine learning directly in on the pieces of silicon. So we create the silicon with machine learning on it, and we install it in the experiment to unlock new experimental capabilities. If we keep wanting to talk about qubits, I may throw in some qubit information in there. But this will be an opportunity where, depending on what we're interested in, we'll talk about future directions. And so this is the plan. So today we talked about intro to the lectures and general ideas. Next time, physics questions, then experimental considerations, then particle identification and reconstruction, triggering for real-time event selection, simulating our theory and experiment, connections to other experiments, and then we'll go into outlook and future directions. So that's all I have. Thanks a lot for coming. It was a great pleasure.